Hello, my name is Alex Landis, and today I'll be delivering a lesson on weather services and weather information and how, as either a commercial or more specifically looking at a new student, a private applicant, and teaching them the basics of weather, the basics of why we need to know weather, and things of that sort. Just fair warning, I have a little bit of a cough, so if that annoys you, I'm sorry, but getting over a little something. So today, again, we'll be going over weather. And why do we need to go over weather? Why is weather so important? Well, unlike other professions where you can just sit inside, sit in a chair, or work from home, or all those other things, you can't work from home in aviation. You can't sit in an office or sit somewhere and not have to worry about the weather. The weather impacts everything that we do in aviation. Whether it be for VFR procedures, whether or not we can fly, whether or not we have the required visibility, the required ceilings, things of that sort, all impact whether or not we can fly. And it also, properties of the weather affect, even if we can fly, how we fly, right? Like whether or not we'll fly direct to a certain place, whether or not we'll fly around weather, where that weather is moving. For example, winds aloft and how they differ from winds on the ground and how they can affect aircraft performance with headwinds, tailwinds, even where we land when we come to land on a runway. That is all weather and wind dependent, right? So unlike any other profession, weather is extremely, extremely important in aviation, and is the basis of really everything that we do, right? So yeah, today that is what we'll be talking about. And the first thing we'll start about is, okay, where do I go to get weather information? So some of my favorite resources, and I would write them down, but frankly, I think it'll take too much time. I'll just show you, take unnecessary time, really. Aviationweather.gov. For a new student, they might not know what that is. For a commercial student, I'm assuming they'd be all too familiar with what aviationweather.gov is. So that's a resource we can use to get things like our GFA tool, which we'll go about in a little more detail later, our METARs, our winds aloft, our TAFs. Aviationweather.gov is a very, very great and amazing resource that we can use to gather all the weather information we need to decide whether or not we want to fly. And ultimately, that is what we are doing with weather, and with the weather information that we're given, is making a decision on what we can do and what we should do, right? Because there are many, many fatalities where people, in general aviation specifically, are not familiar with or have a macho attitude with, and are informed of the real inherent risks and dangers there are with certain types of weather phenomena to aviation. Another important service that we can use is the flight service frequencies that we have. They can give us data even during our flight, right? Flight service can give us weather en route. It can give us weather prior to our flight, right? Exactly. So so on top of aviationweather.gov, we can call 1-800-WX-BRIEF, right? And they can give us all the information that we need for our intended route of flight. Specifically, if we're going around cross country, you can call and say who you are, your aircraft type, how many souls are on board, all those things, and they'll just run you through word for word all sorts of information that we'll go through in a minute. You can call 1-800-WX-BRIEF. You can also go to their website, 1-800-WX-BRIEF.com, I believe, and it will give you all that same information in a written format. So recognizing what weather is just the differences in pressure. There's the movement of the air. All these things are what define the medium air that we fly through, the medium that we travel through. And something that's important to realize is the composition of air. So air is, I believe, 78% nitrogen, 21% oxygen, and 1% other gases, right? And that's important to realize because we usually think of oxygen as something that we breathe in and is the air that is encompassing around us, but it's only not even a quarter, barely over a fifth actually, of all that makes up the air. And the nitrogen kind of stabilizes the air, and there are other gases, and the other 1%. In a weather class I took, they actually recognize that water vapor is less than 1% of the air that we usually fly through, but it makes up so much of what we do. That water vapor that makes up the clouds and all sorts of other things, it can obscure our visibility with fog, with haze, with mist, with all those things can obscure our visibility, which would be a reason to go or to not go on a flight, right? Or the cloud clearances and the cloud levels. That is also a ceiling, is what we call, and we'll talk a little more later about, is what allows us to go or to not go legally. We obviously don't want to break any laws. And with VFR, that is obviously something that is very, very important, is visibility, right? Visual flight rules. We're hoping to be able to see and have conditions that allow us to see during those phases of flight. So with that water vapor being a small percentage of the air that we actually walk through, breathe through, fly through, that is something important to realize, that even such a small amount of water vapor can make a big, big difference on the weather that we are participating in and that we are experiencing firsthand, right? Wind is also vital, very, very, very important, and that is a medium and it's defined by the pressure gradients, low pressures, high pressures. For a private applicant, just as a quick side note, I might not hit on pressurization and high pressure and low pressure systems as much. I would definitely touch on it, but that would definitely be more of an in-tune concept for a commercial applicant. But anyways, those high and low pressure systems are very important in directing the wind, right? Because with the wind being directed and drawn to inwards and counterclockwise to a low pressure system, and outwards and clockwise in a high pressure system, that's going to determine kind of the direction of where our winds are going, right? So right here's an example of how winds would be working around a low pressure system, right? It goes in a little bit, right? You have weather in, the wind's coming in, wind's coming in, wind's coming in, all the way around, right? And that's kind of how the winds revolve around a low pressure system. And the opposite can be said about the high, right? A high pressure system where we'll have air going clockwise and out, right? So we got it going like this, right? And that's going to affect, right, where it goes, all of our wind and how it goes around a system. And that's important to understand because let's say our airport is here, right? Say we're right here, our airport that we are interested in is right here, right? So effectively our wind would effectively be coming from this direction, right? We have wind coming from this direction. So with the properties of air and how we fly through, why would that be important? Why would the wind direction be so important to our flight operations? And side note, for the commercial applicant, I would hope that they'd be able to realize, okay, the direction of wind on the ground at an airport would determine which direction we're taking off from, right? So for Lafayette, right, we got 2810, right? Got 2810. We got 2, 3, and 5, right? We got 5, 2, 3. And we got a wind coming from this direction. We're going to want to take off into this way, right? Into the headwind. And that's important, again, because a headwind determines our takeoff and landing performance, right? So when we take off into a headwind, as we should always try to do unless in an emergency situation, that will decrease our ground roll and that will increase our takeoff performance, right? We'll have shorter runway lengths, and that will allow us to use the least amount of runway possible because we don't want to use the full length of the runway, right? We want to be well within our limits, right? For some people, you want to take that landing performance data that hopefully we have covered in a different chapter, or not in a different chapter, a different discussion. And depending on your experience level, your personal minimums, all those sorts of things, some people take that landing distance or that takeoff ground roll distance, and they'll multiply it by 1.5 for safety reasons. And for a private applicant, for me to send them solo, I'd probably double that distance. And that was only if I'm, willing to send them solo to begin with, right? So we want to have all the runway available as much as possible, right? So that's why we take off into a headwind. And same thing with landing into a headwind. That will also shorten our landing distance, right? And that will allow us to use the least amount of runway as possible. So that is another thing that's important about weather is how it affects where we take off from. That's a very, very simple thing to be able to see. Another component that's very, very important for us to understand is a crosswind. So there will be very few times where we'll have one of these runways, right? Where we'll have a direct, wind from 280, right? That would be ideal, right? We want a direct headwind, but that's not how our world operates. And we obviously don't have a runway for each and every one of the headings, right? We don't have a runway at 3, 6, 0, 1, 2, 3, 4, 5. That's not how life works, right? We have at Lafayette, we have 2, 8, 2, 3, 1, 0, and 5, right? And to show those things, I mean, the important distinction is that you're gonna have situations where you have crosswinds, right? You're going to have situations where you have a wind. Forget these high and low pressure systems. You'll have a wind for whatever reason that will come if, let's say, for example, I had a situation in 248 when I was flying with an instructor. And we were flying at night. It was a night cross country. I believe we went to Indy. I forget where else. But where you'll have the 2, 3, 5, and then 1, 0, 2, 8, right? You'll have these. But for whatever reason, on the day that we chose to fly, we didn't have the landing lights or the runway lights on this runway, right? So this runway is out of the picture. We didn't have those. We couldn't land because we couldn't see the runway at night. So, and on the same night, we had a low-level wind shear, and we had very, very, very gusting winds. We weren't going to fly in those conditions. We looked at the TAF, which again was another material, another item that we will look at. And it showed that those winds would not be prevalent. They would not be active until well beyond when we were supposed to fly. But for whatever reason, winds moved up. We had that gust. I think we had at one point it was like, and because we lost this runway, right? We can only land on 2, 3, or 5. We had a direct, almost completely direct crosswind, gusting at about 25 knots, right? Which is a lot with those shifting winds. And all things of that sort. So we could only land on this runway, which is definitely not ideal, right? I forget what the wind direction was exactly, but we were landing on runway 23 because that's the runway that had the lights, and we didn't want to land from the other direction. So having that, having those gusting winds and that crosswind was not ideal, right? And because when we're landing, we're coming into land, if we have a wind from this direction, right, then we're going to have to compensate by crabbing into the wind and using effectively almost at that point a fully deflected rudder, right, into the direction of the wind. And that can cause all sorts of problems. That can cause us to go off the runway if the winds are extreme enough, especially if they're gusting. That can cause us slow airspeeds sometimes if the winds are gusty. Our airspeed cannot be fast enough to keep us in the air, right? All these complications come with crosswind landings, which are hazardous to flight. So it's important to understand all of these nuances of wind and the weather and what affects them, right? And I've gone into a long explanation of that, probably a little too long. Gusting winds. So like we talked about, I touched on it a little bit. Gusting winds are winds that change direction. Or not, sorry, that's not true. They're winds that change severity, if you will. They'll change. They can go from 12 consistent knot, 12 knot consistent crosswind to gusting to whatever wind that would be. Let's say gusting 20, right? That means the wind can stay consistent at 12, and then at one point or another, it'll gust up to 20 or so knots, or whatever the gust is. That's important to realize as well, and that can be something that we look at when we look at whether or not we're going to fly that day. So, or how gusty are the winds? How much is the crosswind component? At Purdue, we actually have a crosswind chart, which will show us whether or not we are even allowed under Purdue policy guidelines to fly. With different limits for a solo student, for different limits and where you're on your course progression, and different limits for when you're with an instructor, right? So all those things are things to be taken into account. A tailwind, right? So an opposite of a headwind, effectively. Tailwind in the air on a cross country, great. Tailwind when you're coming into land, not so great. This is something that you do not. It will increase your takeoff and or landing distance, right? Which are things that we do not want. It can also cause for some instability upon approach. Tailwinds are not something we want to land into, something that's an amazing, amazing thing to have on a cross country. And so there's all sorts of things. I mean, mountain turbulence is another thing that we don't necessarily deal with as much at Purdue, being in the flat Midwest with nothing but good old corn all around us. But somewhere in the, in Colorado or in California or places like that, where there are those mountains, that is something important to understand. Understanding that there are mountain waves that come off of mountains that can cause severe downdrafts and other things that are not very conducive to wind, aren't conducive to flight, I should say. And so those are all things to consider when we're considering weather. Those are all things that we should take into account. There are other things like dew point. Dew point is the saturation of the air, effectively. So we'll go over this more in detail as we go on, as we cover METARs and TAFs more specifically. But when you look at the dew point, it'll look something like this. Let's say 15, right? And so this is temperature, right? And this is the dew point. So the temperature dew point spread we'll cover more in detail later. The closer these numbers are together, the more saturated the air is, right? So this number right here, the dew point number, is the temperature at which the air will become fully saturated. That means it holds all the water that it can. You can't have a METAR or a temperature dew point spread that looks like this. You can't have a greater dew point than a temperature, right? So it's important to understand that the temperature dew point spread is the saturation of the air, which will also give us an indication of all sorts of weather phenomena, right? Clouds and cumulonimbus activity, right, or misting, or things that will inhibit our visibility or our ceilings will usually occur at a smaller spread. When those numbers are closer together, we will see more of those phenomena typically, but that doesn't mean that in and of itself is going to be the sole factor for why we have weather phenomena and weather occurrences. Clouds. There's many different kinds of clouds. Cloud coverages is something that's more important to our level in aviation as aviators and as professional pilots. It's important to know coverages, but there are also different types of clouds. So there's the cumuliform clouds, right? Cumuliform clouds, that is abbreviated, cumuliform. Those are going to be your more billowy and your more full clouds, I guess, the more fluffy looking ones. And those will be more responsible for unstable weather. But why is that? Why would these fluffier clouds be more responsible for unstable weather than, let's say, like a flat stratiform cloud that we'll talk about in a minute? Well, the reason for that is, first of all, there's little to no chance I would expect a private applicant to know that. Potentially maybe for commercial, maybe not. But what's important to understand about what these billowy cumulus clouds show us, here I'll put it here, cumulus clouds, right? Cumulus. And then stratiform over here. This is strat. These cumulus clouds are going to have something that a lifting motion, right? That builds up these clouds, right? That makes it unstable. You're going to have all this air that pushes these clouds up and builds this cloud. So when you see these big fluffy clouds, that means you're going to have this upward draft. You're going to have this motion that builds these clouds, right? And that's what makes it for a unstable atmospheric conditions, is that you have to have this updraft in order to build these clouds. Whereas these stratiform clouds, there's not that upward motion. You're not having this built up, right? It's just calm. That's usually what you'll find with stratiform clouds, is that you'll find calmer conditions in the weather. One thing that will impact flight, though, and flight decisions of stratiform clouds is that they can usually be accompanied by low visibility conditions. And for VFR operations, we need to be able to see, right? So the stratiform clouds might not be as turbulent, but they will be lower visibility, and cumulus clouds will have more of a clear atmosphere typically, unless you have a cumulonimbus cloud, nimbus cloud is just really raining cloud is nimbus, and cumulonimbus is these big billowy clouds that are raining, right? And that might affect your visibility a little bit. So those are the two main differences between stratiform and cumulus. Cumulus, you have this building, this updraft, and stratiform will be a lot less advection and a lot less of those variations in the winds and stuff like that. But it'll typically be accompanied by a lot lower visibility. Turbulence can also be accustomed or go hand in hand with thunderstorms, and thunderstorms are definitely something that we need to be looking out for as aviators. Thunderstorms are something that we should obviously stay away from. Other than them having not a nice appearance, they're also not nice to fly through. It's something that we want to stay away from. Again, with thunderstorms and cumulonimbus clouds, you'll have concurrent updrafts and downdrafts depending on the stage of the thunderstorm. You'll have a dissipating stage so you have the building stage where everything's kind of building up, and then you have the mature stage where you have updrafts and downdrafts, and then you have the dissipating stage where actually there'll be heavy downdrafts because it's dissipating, right? It's getting kind of red, and they can have those three stages, but they can build on each other. You can have building, and then you can have mature, building, mature, and it kind of builds on itself, and that cycle can last for a very, very long time. And that is something that we should not be flying through. We should not be flying through thunderstorm activity. And another thing with thunderstorm activity can also bring on things such as hail. Hail and stuff of that nature can actually, believe it or not, it can disperse, if you will, from a cloud up to 20 miles is the recommended distance that we should be away from a thunderstorm. So when we're navigating around, it's not like we're just bobbing and weaving really tight in here. That we should never do that around a thunderstorm. At the very minimum, we should try to be 20 nautical miles away from thunderstorms for reasons like hail and cloud lightning and things of that sort. And with the stratiform clouds again, and with the low visibility, we'll have things like fog. Fog are inhibitors of visibility for sure. And there are different types. There's advection fog, which form as warm air moves across a cool surface. And a great example of that is in the lakes, right? Or lakes in the oceans, you'll have warm air, maybe from the coast or whatever. Like let's say this is California, or I am terrible at art or terrible at drawing, so let's just say we have this land mass right here, right? So this is the land, this is the water, right? And you'll have warm air maybe coming off of the land, right? And it comes in contact with the water, which might be a cooler surface, or vice versa, and you'll have fog that will build up because the warm air comes across the cool surface, right? So I don't know if you can see that, but and then the next type of fog is radiation fog, which actually usually forms during calm and clear nights, right? It's again, radiation fog occurs when the ground cools and the air is still warm, right? So late at night, you have the moon out, right? It's late at night. Again, terrible artist in part, but you'll have be it at night, these stars, all these things, and it'll be a cold, cool, clear night. It's important to realize it's clear. It's usually when radiation fog is formed. And you'll have this fog form along the ground when the warm air comes in contact with a colder surface. And then you'll have things such as upslope fog, evaporation fog, ice fog, which is just small crystals of ice effectively form. And other obstructions of visibility that aren't necessarily as common for us are volcanic ash, which is something that we might not see a lot, especially if we're looking at a METAR or something in the state of Indiana. I would be very, very shocked if we ever saw volcanic ash. But for other places that we fly, we need, as aviators, as professionals, we need to understand whether that might not be common to us. I've seen many, many case studies in my time at Purdue where the main cause of the accident that could have saved the pilots' lives was their misunderstanding of the weather that they were in. You'll have, I watched a case study the other week where there were two pilots. One of them had his ATP, which requires a lot of experience to be able to obtain, a lot of knowledge, and he was flying from California to Colorado. And he was flying from California back to the East Coast. They refueled somewhere in Colorado. I forget exactly where, maybe Aspen, somewhere really, really high up. And they weren't familiar with the terrain. They weren't familiar with the composition of the air and how air at higher altitudes is a lot thinner, which degrades the performance of the aircraft, right? So understanding not just the weather, but the air that we're in and all those things can be life or death. So that is something that is really important that we need to understand. So volcanic ash, you might see that on a METAR someday. You never know. Haze, smoke, forest fires are a big inhibitor to visibility, and that can stretch out for miles. It can affect a lot of people. So those are all things that we need to understand as aviators. Other things that we need to understand: air mets. Air mets are area forecasts. They happen every 6 hours for the necessary regions that it applies to. There are three types. There's the Sierra. Let me clear this off really quick. There is the Sierra, and I'll abbreviate these because I don't want to waste our time. Sierra, Tango, and Zulu. So these are air mets for IFR conditions, right? Sierra typically encompasses IFR conditions. Then Tango is issued for low-level turbulence. Low-level turbulence, so I'll abbreviate that. Low-level turbulence. And other important factors such as wind shear, surface winds, all the good stuff that will affect our winds in flight. And they also have icing and freezing levels. And icing icing and freezing levels are important to realize because icing has a huge impact on the aerodynamics of our aircraft. Icing is in conditions can, I think it's up to, it'll decrease our lift by up to 40%, right? Which is astounding. Like if we lose almost half of our lift, or almost a third of our lift, or whatever that number is, or even less, it's huge. And not only it's both. It's not only so the two factors that impact our plane flying through the air is the lift that's generated, as well as the drag that is imposed upon it. And not only does it reduce our lift, it subtracts lift by up to 40%. It'll also increase drag by up to 50%, right? 50% drag plus drag, right? And it'll decrease our lift by up to 40%. That's astounding, right? That can cause us to fall out of the air in such a manner where we can't control it, right? So those are very, very important for us to understand is those air mets that are included in our area forecast by the air mets, right? By our air mets. Air mets. It's very important to understand because wind shears can affect where we land, how we land, if we should even be able to fly, if we should fly based on our personal minimums and university policies or even FAA guidelines. This is the Sierra with the IFR conditions can affect our visibility, which for VFR pilots impacts whether or not we can see, which is important because we're flying under visual flight rules. And then obviously with our icing, whether or not our plane can actually fly through the air, that's something that is very, very important. And with that comes SIGMETs, right? And SIGMETs are things that are affected by non-convective weather. And you might think to yourself, well, non-convective weather is probably stuff I don't need to worry about. No, just because it's not convective doesn't mean it's something that is not important, right? With SIGMETs, they include icing, they include turbulence, they include volcanic ash, lower visibility, all those things. And those are all things, right, just like with the air mets, that are very, very important. And it goes non-convective, but important, right? But still important. Again, icing, winds, ice, winds, you name it, anything that's not convective that we should know are involved in the SIGMETs. And those are issued every 4 hours and are important, right? And they have convective SIGMETs. These are the things that people generally think of when they think danger, right? Like they're all these are important. We should know everything about them, but convective SIGMETs are typically associated with thunderstorms, right? So I'm going to say convective SIGMETs. And convective SIGMETs, again, associated with thunderstorms. Thunderstorms. So again, with the lightning and stuff we talked about earlier, that's going to have to do with things like hail. It's going to have to do with the distance, right? We should be, at least 20 nautical miles away from those thunderstorms. And, hail can be flung from them. All sorts of things can happen with convective SIGMETs, right? We want to stay away from those. SIGMETs can have, and they're usually defined by surface winds greater than 50 knots. That's how we'll define the SIGMET. Surface plus 50 knots, right? You'll have hail larger than 3/4 of an inch. Hail plus 3/4 of an inch, right? And you'll have embedded thunderstorms, lines of thunderstorms, anything to do with thunderstorms. Tornadoes is another big one. Tornadoes is huge. Tornadoes are huge for convective segments, and that's where you'll find all your information about that. And in order for it to qualify, you'll have these qualifications for a convective segment. And then PIREPs. PIREPs are important because this is where the pilots provide the weather information, right? So I'll erase all this. Because not all information can be definitively defined on the ground, right? There are things that pilots can report, and pilots can help with PIREPs. Pilots can report all sorts of things. Like off the top of my head, I think it's cloud tops, right? Cloud tops, because when we look at a METAR, which we'll look at in a minute, cloud ceilings are given to us. But okay, how high do those clouds go? Cloud tops are something that can be provided by PIREPs. You can have like severity of wind shear, of turbulence, right? I remember that was actually very, very beneficial on my long cross country for 248 because I was able to distinguish. It was a very, very bumpy day. It was going to Smyrna, a lot going on. I had a whole crew with me. We all flew to the same spot for our long cross country. And there was a pilot that gave a PIREP of, okay, like turbulence at this altitude, but once you get to this altitude, it clears up. And it was good for a pilot who's experiencing it to allow me to say, okay, like if I request, with my flight falling to climb above this turbulence, I can get out of this condition where I'm hitting my head on the ceiling every single time. Or even more dangerous. Sometimes, moderate, severe turbulence can really, really affect your flight conditions. So things like that are reported in a PIREP, right? And beyond that, we have all these abbreviations that we'll see in PIREPs. We'll have all these things. We'll have stuff that I will include a link, or if I had a student, I would show them a list that I would expect them to either print off or have access to, so that if they ever see an abbreviation that they don't understand, they would know where to get the information to find what they need to be looking for, right? So with that, PIREPs also include your flight level. They'll include flight levels. They'll include sky conditions, right? Like ceilings, tops, all sorts of things like that. They'll include weather, right? Weather phenomena, turbulence, icing, remarks, all sorts of things. Icing, remarks, all the good stuff. Remarks, right? PIREPs can be very, very useful when we don't completely understand. And really quick, a distinction that I want to make that I don't think I've touched on yet with icing is the types of icing. So in flight, we could have either clear icing or rime icing, or rime. Both are impactful and detrimental to flight. And rime icing, or we can also have a mixture of the two. But rime icing is icing that is more occurs more with smaller rain, like mists and stuff that freeze to your aircraft. It's rougher in texture, whereas clear icing is more it's icing that's harder to see, harder to notice, but that's what makes it dangerous, is that it's harder to see. And if you can't see the icing and it accumulates, you'll have that increase in drag and that decrease in lift, which we obviously don't want. So if at all possible, like it can even be formed with moisture that you've built up on the ground, in terms of like moisture that's built up on top of like fog, or in the mornings you can have accumulation of water on your wings. That can freeze in the air, and you want to obviously wipe that off, and you want to avoid those icing conditions at all costs. So yeah, those are the different things that we can include on a PIREP. And we will definitely see those to come, and it will come with practice, and you'll become more and more comfortable as you see them more and more often, and you become more and more accustomed to them. Now, I'm going to use my iPad really quick right here to go to aviation weather, and we're going to pull up a METAR, and we're going to walk through it step by step, right? So I'm going to write this down. We're going to walk through it. So we're here. 221754 Zoom. 12 custom. Cast 040 1809 A1. And then we'll start there for the private student. This is the information that I would expect them to know upon the completion of this lesson. So breaking it down line by line, we'll start here. This location, right? So what a METAR is, it's weather at a specific location, right? So it's not a huge, wide-ranging forecast. It's a weather at the airport of interest. So today, I'm interested in the airport that we'll probably be using more than likely, and the airport that I have flown at many, many, many times, as I'm sure, as I know, many other students have as well. And this location, right? Lafayette is where we're flying out of. And this K right here is the country identifier, right? The first letter is always going to be the identifier of the country you're in. So sometimes you might see, P. That would be the Pacific, right? So that's Hawaii. I think HLL, I believe, is Honolulu. I could be, or HNL. Either way, even though it's in the United States, it's not in the continental United States. So everything with a K is going to be an airport within the continental United States. And sometimes you'll see an M, and then whatever the abbreviation is, it'll be Mexico. Whatever the case may be, this first letter is our identifier, our country identifier, right? And then the following is the airport that will be at, so Lafayette, right? And then for the next line, for this line right here, this is our date, right? So it's the 22nd of the month. So when you go 23rd, 24th, so on and so forth, and you get to the end, you're just going to reset. It'll be the first of the month, the second of the month, the third of the month. That's what these first two digits are, is the time of the month. This is the hour. This is the minute, right here. Hours, right? Minutes. In Zulu, right? In Zulu, which is important. Zulu is a universal time. In the East Coast, depending on whether or not it's daylight savings or fast spring forward or whatever you like to call that, it's either 4 or 5 hours ahead of where we are. 4 or 5 hours, right? 5 hours ahead of where we are. It's an important distinction with Zulu time. So, and this is all obviously military time as well, so it's not going to be PM, AM, all those things. So it would be 1754 Zulu, since we're 4 hours ahead. That's around 3:54 Eastern time, right? So you subtract the 4 hours since we're in the spring forward time, and as we get past the daylight savings, then it would be 5 hours, and then it would be 2:54 Zulu, right? Is when this weather observation was taken. That's not the current time. This information, all this information, was taken at this time. This is the time it was valid. This is the time where they took all this other information. Now, for this next part, this is our wind direction, right? So the wind is coming from 130. You could look at it even as like degrees, right? That's not included in the METAR, but that's the direction. And this next one is the winds, right? So the strength of the winds, right? So we have 12 knots. That's our strength of winds. Gusting. You won't see this all the time, but today we've seen this is a great learning example. gusting, so it's 12 knots to 19 knots, right? 12 to 19 knots. So 130, direction, those first numbers. 12 gusting to 19 knots, right? So that's important. This next one is 10 statute miles of visibility. This is how far we can see. You will never see this, the METAR exceed 10 knots, right? Or not 10 knots, 10 statute miles of visibility. You might see that anything less than 10, but nothing greater than 10, right? 10 will be the greatest thing you see. So it's not there's actually 10 miles of visibility, it's there's 10 or more, right? That's what that's telling us right there. And that's important, again, to understand because visibility requirements are very, very important for go, no-go decisions, right? Overcast, right? So we have different layers, and this is also actually important to cover. In sky conditions, right? So sky conditions, we have few clouds, scattered, right? And those are not ceilings. Those are not ceiling requirements. So whenever you see few or scattered, those aren't ceilings. Now, however, what are, or you'll also see sky clear, which is obviously not a ceiling either. But broken, or overcast, right, are ceilings. Those are things that we cannot fly as VFR students or VFR following pilots. We cannot fly through broken or overcast systems, and that's usually for the scientific. A broken is usually about 5/8 of the sky coverage to 7/8 of the sky coverage. That is broken, right? So the clouds are covered, if you see broken, with either 5/8 to 7/8 of the sky is covered in clouds. And an overcast is just everything, right? Overcast is you can't see above them. That's what we got, right? It's just clouds, more clouds. It's overcast. So those are ceilings. So here, it's overcast at 4,000. So that means as VFR operating pilots, we cannot climb above 4,000 feet because that's where the clouds are. That's ceiling, and we can't go anywhere above that. All right. And for this last little bit right here, is the temperature dew point spread, right? So as we talked about earlier, this is given in degrees Celsius. This is at 18 degrees Celsius, right? Degrees Celsius. So temperature. And the next one is our dew points, which is 9 degrees Celsius. And then this is where the temperature at which the air is saturated, right? So the air is obviously not saturated today, or at least completely saturated, because we have not gotten to that that dew point. That temperature dew point spread is far enough where the air has not been saturated. And the last one is important. It is our altimeter, right? And that's very important because that helps us set our altimeter setting, which will help our instruments measure how far we are above the ground or at MSL, above ground level, all those things that help us calculations of, okay, so I need to set my barometric pressure to 30, right? 0.31, 30.31, right? And I believe that is in inches of mercury. And that will show us, that will be important for our altimeter in our aircraft. So this is all the information that is important for us to know. So if an example of a go, no-go decision would be, okay, I want to do steep spirals, right? I want to go up to 5,000 feet, and I want to do my steep spirals, right? Would I be able to go that day? If my whole purpose and intent was to do steep spirals at 5,000 feet, would I be able to do that? The answer, hopefully commercial students, since they're actually practicing those, would understand, would be no. Obviously, I cannot go with VFR, operating VFR, if the ceiling is overcast at 4,000. I can't do that, right? And depending on our wind clearance and limits and whether or not you're comfortable with your own personal minimums, I might not even be able to go because of the wind gusts. Now, it's only a third, so we'd probably, given this weather information, we'd be going on runway 10. So it would only be 30 degrees off of our runway heading, but that's enough to do a crosswind where I would not send someone on their first solo doing that. Let's just say that. Probably not. I'm not experienced enough as an instructor, obviously, but that might be a limiter as well, right? So we can look at our winds. We can look at our visibility would be huge, but visibility is fine today. We can look at our ceilings. All of those things can help us determine whether or not we will fly. Right? We should fly. We will fly. Or we want to fly. Right? All of those things are very, very important for us as aviators. Right? So back to what we were talking about. We got the METAR. We also have things like TAPS, which will also help us project kind of the weather that we are looking at, the weather into the future. Right? So a lot of the same principles of the METAR. It'll have winds and it'll have ceilings and all those things. The difference is you'll have from lines, which will tell you the weather is from this time to this time, we are expecting this, right? We'll have from. You'll have becoming. You'll have, okay, weather is becoming this. You'll have temporary restrictions, which can change in the middle of an inline of a TAF, right? And I would walk a student through what those things individually look like, but I won't waste my time here. And then there are also for cross country specifically, weather briefings and which kind of briefings you'd use. So standard briefing is the briefing you use. It'll tell you all the information you need to know, and it'll tell you weather synopsis, current conditions, en route forecasts, destination forecasts, winds aloft. All of those things are included in a standard briefing. You'll also have an outlook briefing, which is, so the standard briefing is weather within 6 hours of your current time, right, of the time that you obtained the weather information, right? And then you'll have an outlook briefing, which is anything beyond 6 hours. So if you want to look ahead and start planning ahead, you look at the outlook briefing, which you should not go on because that is not current weather conditions. But then you'll have also an abbreviated briefing, which is just an update to the outlook briefing that you have gone over in order to get that weather information potentially ahead of time. That will update you on that weather information. So you should not make a plan based on the abbreviated or the outlook briefing, but you can use the abbreviated briefing to update an outlook briefing. But typically you would like a standard briefing for weather, either over the phone at 1-800-WeatherBrief.com or over the phone at 1-800-WeatherBrief, WXBrief, or 1-800-WeatherBrief.com for an online source. And then we have ATIS and ASOS and AWOS. And so an ATIS is something where it's at a towered airport, and it'll give you the weather. It will give you time in Zulu, winds, visibility, cloud coverage, temperature, altimeter settings, and other information, NOTAMs, airport remarks, and stuff of that sort. Birds in the vicinity, I hear that all the time, drone activity, all sorts of the things that you'd want to know at a towered airport that ATIS will provide you. And it'll give you information. It'll give you an information. It'll give you with Bravo or Charlie, and those are things that you'll tell the airport. Okay, like I have information Bravo, and that will tell them that okay, like all this weather that we have, we know that he has it because he has the information, right? And AWOS, right, is updates every minute. That's important. So with an ATIS, it's important to understand that maybe like 5 to 10 minutes at the end of every hour. That line might be dead when you're listening, right? That might be because they're updating the ATIS. Well, with an AWOS, that is updated every minute. That's the difference with an AWOS and an ATIS. An ASOS updates every hour. So an ASOS is usually something that we'll have at a untowered airport, and then we'll come in and they won't give us a an information phonetic alphabet letter to go along with it, like an ATIS would. So you would say, like, okay, if I'm at Frankfurt, I would say, okay, Frankfurt traffic, I have the weather, right? Or something of that sort. Or I have the weather for Frankfurt because it's specific to that airstrip specifically. So in conclusion, with all these things, with all the low-level wind shears, convective activity, sigments, convective sigments, icing, all those things, we can take all those things into account as to whether or not we will go. We'll make a go or a no-go decision. And on top of that, we might look at personal minimums, like I'm safe. Do I have any illness? Do I have any medications that I am using? Do I have anything, an underlying stress? Do I have alcohol consumption within or out of minimums? Do I have I eaten? Do I have any emotional responses? And those are all things that can indicate whether or not we will or will not go. So recognizing these things as hazardous is very, very important. Analyzing and understanding how to analyze this weather information is very important. We want to understand, okay, with the METAR we were looking at earlier, it was, I believe, OVC 040, right? That's not overcast at 40 feet, right? You're going to add understanding that's overcast at 4,000, right? And those kinds of things. Understanding the information that we're provided is crucial to what we do as aviators, right? And how we correct ourselves based off of that. So at this point in the lesson, I would probably go through various different examples of weather in the METAR, quiz them over it, look at METARs in maybe surrounding airports or airports all around the country, and just give them the simple METAR and say, okay, what does this mean? What does that mean? On the basis of time, I will not do that. But yeah, that should do it. That should cover aviation weather. And hopefully, I would hope that the student have gained from this that the ability to determine whether or not we will go or will not go, or what conditions are safe, and how to use the resources at our disposal to determine whether or not we are safe to fly. Thank you.